Here we are. These are notes for section 5-6, solving systems using matrices. You are going to love this section because it's going to save you a lot of time. Okay, we are going to learn how to solve either a 2x2 or a 3x3 linear system by using a matrix, and it'll be a simple command that will actually solve it for you. Okay, this is a very fast way to solve systems. I like it a lot. But again, you need to know those other methods because you're not always going to have technology available to you to do this on your own. Okay. First of all, what you need to know is that this is a system. We can write it using matrices, okay? This is called a matrix form of a system, or a matrix equations. This is a way to write it out, okay? It has 3 parts. You need to know these parts. This is the coefficient matrix. This is the variable matrix. And this is the constant matrix. Now, they didn't get very creative with the names. I know it's kind of disappointing. But this should make sense to you. This is called the coefficient matrix because look, 3, -1, if I put a 1 in there, 2 and 4. Oh, look, those are the coefficients. The variables here say x and y. Guess why? Oh, look, the variables are x and y. And 14 and 0 are my constants. This is matrix multiplication equation. You can see that this does work out. 3 times -1, x and y. Do you see this? 3x minus y. That's exactly what that is. Okay, and it's going to equal 14. That's the equation I have. 2 times, not 2 times 4, 4 times xy. We're done with this one. 2x plus 4y equals 0. Okay, this is just another way to write a system. It's not hard to do. You just need to remember the process, and it should make perfect sense to you. Coefficients first, then the variables equal the constants. Okay, so let's look at this. Go ahead and expand this to verify that it represents the following system. And that's what, is that the same one that I just did? Yeah. Okay. Again, you take the 3 times and the -1 times the x and the y. And usually when we do this, it would be 3 times x, and then you'd add the -1 times y, and it will equal this top number. Well, that's the same thing as 3x minus y equals 14. That is the first part of the system. 2 and 4 times x and y, we would have 2 times x plus 4 times y equals 0. 2x plus 4y equals 0. So that's why it works. That's why we can write things this way. And you'll find that this is a very helpful way indeed to write these systems, because then we're going to be able to solve for this variable matrix, and that's going to tell us what x and y need to be. If this was a regular equation where it said 2x equals, let's just say it said 14. Let's pretend the constant was only 2 and it just had 14. We could get x by itself by dividing 2, divide by 2, and we all know x equals 7. It's going to work similarly with these matrices. This times this equals this number. These are the variables. That's what I'm looking for. So I'm going to get them by themselves by moving this, and we'll show you how in a second. Okay? How do we solve? Well, we have to get x and y by itself because those are the variables that we are looking for. And to do this, we need to get rid of or move that coefficient matrix. We multiply both sides by the inverse, and it is very important that it needs to be on the left. It definitely does matter, okay? So like going back to that equation that we just had, 3, -1, 2, 4. xy equals 14, 0. All right. How do I get x and y by itself? Well, this is the person I need to move. How do I move it? What I can do is I can take it times 3, -1, 2, 4 inverse. And it has to be on the left, so I have to do it to this side on the left. And the reason it has to be on the left is because matrix multiplication is not commutative. We talked about that before. You can't go back and forth. And when we take the A inverse times A, like if this was A and this was A inverse, That gives us that identity matrix, 1, 0, 0, 1, because an inverse times itself is the identity. So now I have 1, 0, 0, 1 xy times 3, negative 1, 2, 4 inverse, 14, 0. Okay, so it has to be on the left because it's not commutative. So you need to tell the equation, do I want this multiplied on the left or the right? And we are working on the multiplication on the left. All right, well, we can actually calculate this all the way if we want. We are going to use graphing utilities mostly, but I do want to do one by hand so you can at least see it. I don't think I ever expect you to do it by hand like on a test or quiz. But let's see here. First, I need to find this inverse. What is the, can I call this A? The inverse of A is going to be the determinant. Well, let's see what the determinant is. 3 times 4 is 12. 12 minus negative 2, that becomes 14. I'm going to erase my circle. I don't know why it's such a big eraser here. It's kind of ridiculous, actually. Make it a little smaller. I didn't need it that small either. Okay. So I have the determinant is 14. So now I have 1 over 14. We're going to switch these. So it's 4 and 3. 1 and negative 2. Make those opposites. 4 over 14. That's 2/7. Negative 2 over 14th is negative 1/7. 1/14 and 3/14. Okay, so I'm going to multiply both matrices on the left by this matrix. This is A inverse. So I have 2/7, 1/14, negative 1/7, 3/14. Okay, let's see what I have here. 3 times 2 is 6 over 7. 1/14 times 2, this becomes plus 2 over 14. Okay, 6 over 7, that's the same as 12 over 14. 12 over 14 plus 2 over 14 is 14 over 14, which is 1, which is exactly what I expected to happen. Take it times this guy, and I got negative 2/7 when I multiply, plus 4 over 14. That would be 4 over 14 negative. Those cancel out and I get 0. And I'm going to get 0, 1 down below. I could show you, but I'm confident I did that right. Now I have xy. Now I multiplied this side on the left by this inverse. So I need to multiply this side on the left by that inverse. To keep things equal, I'm just going to go ahead and rewrite it. 2/7, 1/14, negative 1/7, and 3/14 times the 2 by 1 matrix, 14, 0. And I'm going to get, this will just leave me with xy. Kind of crammed for space. Okay. 2 times 14 is 28. 28 over 7 is 4, 0. Just as 4, because 4 plus 0 is 4. Done with this one. Negative 1/7 times 14, that's negative 14/7, that's negative 2, plus the 0, so I get 4, negative 2. This is telling me that x equals 4 and y equals negative 2, or my ordered pair is 4, negative 2. These two lines that I had on this previous slide are going to cross at 4, negative 2. Okay, these do get sloppy to do by hand. Look at my paper. I mean, hello. I kind of like looking at papers like that because I know that a lot of thinking was involved in that page, but it's not very neat, and I don't think you guys want to do all that work. So we can use a calculator. We know how to do this by hand, but we're not going to do it again, okay? Here's what you're going to type in. You're going to type this matrix for matrix A. People with Inspire, things will be a little bit different, but these are for the TI-84 people first. Take this in for A, solve this one, and enter this one in for B. Okay, so you edit matrix 2 by 2, type in your elements. Edit matrix and B 2 by 1, enter this in. Then when you leave the screen, second quit, you will type in A inverse A, which you won't need to do because we know what this is going to equal. That's going to be 1, 0, 0, 1. But what you do to the left side, you have to do to the right. So if I took this side by A inverse, I need to take A inverse times this side. So what you're going to type into your calculator is A inverse B, and that will tell you what X and Y are going to equal. X will be on the top, Y will be on the bottom. Make sure you write it as an ordered pair so that we know that you're actually solving that system for where they cross. Okay, so we're going to use matrices to solve this. Let's make our matrix equation first. First we start with our coefficient, and you have to be careful because we're talking about x, y, then z. So I have 1, negative 1, 3 with my coefficients. X is 1. There's no y here, so we do need to fill that in with a 0. Z is 2, and down below I have 2, 2, and 1. Okay, that is being multiplied by x, y, z, and that's going to equal 9, 3, 10. Okay, let's store this in as A, this one in as B. Okay, you're going to multiply by the left by A inverse on this side. That will cancel out per se and leave you with the identity matrix. So you need to take A inverse times this side, and you will find that X, Y, and Z should equal 35, negative 22, negative 16. Okay, so that tells you again that our ordered triple in this case, 35, negative 22, negative 16. That's where they would cross if I did graph this in 3 space, which we have never done. You can check these to make sure it's right. This is 35. This middle one's easiest to check. 35 plus negative 44. That's not right. And it's not right because I plugged in the y value here. 35 plus z is negative 16, negative 32 is 3. Okay? TI Inspire people, I will show you how to do these on your calculator. It's a little easier for you on the calculate screen. You go ahead and go to, let me look at my calculator here, menu, and then you go down to matrix. You create your matrix and you type in this normal matrix. And then after you're done, actually what you're going to type in is that 1, negative 1, 3, 1, 0, 2, and I know this is crammed for space, 2, 2, 1. Then you'll go to caret key, then you'll type in negative 1, and that will take the inverse of that, then insert another matrix in 9, 3, 10, and it should give you a response. If you're having any problems with your calculators, you need to make sure you ask me tomorrow. So that's how we use our calculators to solve them. Now, what about this determinant? What happens if it comes up 0? Okay, we know that if it's not 0, it definitely has an inverse and we can solve it. If there is one solution if the determinant is not 0. It determines there is an inverse, so we can solve it. If it does come up 0, that does not mean you can't solve the system. What it means is that we either have no solution or we have infinitely many. Okay, to determine which one, you can look at a t-table or you can graph it. You can try to find a solution and then see if it works in the other. But what you need to do is really, you can't use matrices if it's one of these special no solution or infinitely many. You need to revert back to your old methods, take a look at the graph, see if elimination gets rid of everything. You need to go back to another method because this method will not work if the determinant is 0. Okay, show that this system does not have exactly one solution. Okay, so they want us to write our equation, 6, negative 9, 2, and negative 3. X and Y equals 12, 4. All right, you could type this into your calculator and you're going to come up with some issues. But what you should look at, always check the determinant first. This is negative 18 minus negative 18, which becomes 0. So to show that it does not have exactly one solution, you could say the determinant equals 0. That's showing enough. Now, how many solutions does it have? Well, now you have to look at another method. You could solve for y, which is probably what I would do. Okay, subtract 6x, subtract 6x. So I have negative 9y equals negative 6x plus 12. Divide 3 by negative 9. And I have y equals 2/3 x plus 4/3. I think I did that right. Okay, let's try this guy. Subtract 2x, subtract 2x. Negative 3y is negative 2x plus 4. Divide each and every piece by negative 3. I have y equals 2/3 x minus 4/3. I'm going to make sure that I did that properly. And I didn't. Right here, this should be a negative. And the reason that was a red flag that I checked, it could be that these were parallel and that they just never touched, but it's pretty weird that the y-intercept was perfect opposites of each other, so I wanted to make sure I didn't make a sign mistake, and I did make a sign mistake. Positive 12 over negative 9 is negative 4/3. This is negative 4/3. These are the same line, which means I have infinitely many solutions. The bad thing about videotaping these lessons, you guys can't tell me when I make mistakes. So I have to tell myself. Oh, and I can't even write. Hello. Hello. I don't know why you're doing that. Okay, well. There. Okay. If it would have been opposites, then it would have been no solutions because they would have just been parallel, not the same line. But this is the case that they are the same line, infinitely many solutions. Okay, I'm giving you the gift of math, and I hope you enjoy it. See you guys.